So I'm on page 2 of my handout. So this distribution is not symmetric. If the degrees of freedom increase, as I mentioned here, as degrees of freedom increase, the chi-square distribution gets closer to being symmetric. So first of all the values, as you see in part D, all values have to be greater than or equal to 0. And it depends on the degrees of freedom. For some degrees of freedom, it has this shape. For others, it has this shape. For others, it has this shape. But as you see, as degrees of freedom increase, it gets closer to being symmetric. But always greater than or equal to 0. It's not symmetric around 0, like for example, Z, right? So Z has this graph, the standard normal. It's centered at 0. But this one is not. All chi-squared statistics, so all chi-squared coming from any sample, have to be greater than or equal to 0. But here it doesn't have to be. Z could be a negative 0.2. It could be 0.3. And so on and so forth. Okay? So it depends on the degrees of freedom. Of course, we go back to the contingency tables. So if I have a contingency table, let's say, with 2 rows and 3 columns, as an example, degrees of freedom, and I mentioned it on my handout in part B, they will be calculated as 2 minus 1 times 3 minus 1. So the number of rows minus 1 multiplied by the number of columns minus 1. So this will be 2 minus 1 is 1, 3 minus 1 is 2. So this will be 2 degrees of freedom for the chi-square test. So I left some room here for you if you'd like to fill it in. These are the graphs of different chi-squared distributions, depending on the degrees of freedom. So now, if we are asked to find the chi-square values, for example, and that is the table, and it should be, since we already opened it, it's I also entered it as a separate table for you, so you don't have to scroll down. It's up to you. So I'm hoping that you are looking, or let me open this. Maybe I should share my screen so you can see where it is. I'm sharing my screen right now. Share. Okay, so here it is. You go to modules, and once you scroll down to syllabus, class policies, schedule, etc., and formula sheets, I entered it, so it's the complete list is right here, but I entered it separately as well for you to find the chi-square distribution table. Okay, and careful again, in this book, we are given, so based on the number of degrees of freedom, and we're going to have an exercise right this moment, these are the numbers of the critical numbers for the chi-squared. Okay, so for example, for let's say 5 degrees of freedom, the area to the right of 0.995 is 0.412. Okay.
Could you say that again?
Yes, yes. So for example, for 5 degrees of freedom, the area that is to the right-hand side of 0.995. So in other words, if I want to determine this area that is shaded in for 99.5%. So this piece is 99.5%. So then this area is 0.412. We're going to look at an example with 18 degrees of freedom. But first we have to graph. So I'm going to stop sharing because I need to show you how we graph and where the numbers come from. So let's take a look. Okay, here it is. I hope you can see this. Yes, I think you can. So we have the first example, example 2 for today. It's number 2, but it's our first example. So here's the chi-square distribution for degrees of freedom 18. So I don't know exactly how it looks like, but it's something similar to this. It's not this because the degrees of freedom are more than, so these kind of, the shape of it looks like this, like an exponential function with a base lower than 1. So this kind of shape is for small degrees of freedom. But this one is larger, so it should look something like this. So we are asked to find the chi-square values that separate the middle 95%. So I'm going to say that, okay, so this is the middle 95%. So if it's the middle 95%, this piece has to be half of 5%. So this is 0.025, and this has to be also 0.025 because this area has to be 5%. If the middle part is 95, this total, this plus this, has to be 5%. So now we are trying to find these chi-squared, but what do I have to the left? I have 0.95, which is this area, plus 0.025, which is 0.975. And I will obtain this number. For the other one, the area to the left is 0.025, so I will determine this value, this chi-squared. Let's go back to the table. And let me share. So this has to be a number greater than this. You agree, because this is 0. This has to be a number greater than this, for sure. So this area is 0.25, and this is the 0.975. Now, with the table the way it is presented, this is the area of 0.975. So I'm just going to shade it in green. So the green area is 0.975. So let's take a look. I'm sharing now. Where's my button? I got it. Okay. So looking at 18 degrees of freedom, here it is. Let's go back up. So I want this area, according to the top of the table for each column, I want it as 0.025. So the area of 0.025 is right here. I go down to 18 degrees of freedom, and I read 31.526. 31.526. The other one, the shaded area, is 0.975. I go down to 18 degrees, and I read, yes, it's correct column, and I read 8.231. I'm going to stop sharing. So The middle 95% in this particular distribution, with the information we have, is between the chi-squared critical value of 8.231 right here and this critical value of 31.526. And they come from the table for critical values for chi-squared. Okay, so now let's perform these two tests. The test for independence, they are the same in many with respect to different the table is used, so I'm going to put them side by side so you see the difference between those two. They are both the same test, conducted in the same way. So this one is for the chi-square test for independence, and this one is the chi-squared for homogeneity. This one is for proportions. Okay. So conditions of the test, the hypothesis will be different. So let's write the hypothesis first. The test will be conducted in the same way. So here it's the variables are independent. Here they're not independent. Here proportions, depending on how many I have, I can have 2, 3. So let's say P1 equals P2 equals P3 from 3 different populations. Here, at least one of these is different. So the test for independence, variables are independent or not independent. The test for homogeneity, for proportions, no difference. The proportions coming from 3 different populations are identical. Here, the alternative, at least one of them is not equal to the other 2. As I mentioned, the test statistic is conducted in the same way. Both of them, I'm not going to write it twice. I'm just going to write a chi-square test. So you do not have to determine the test statistic in this way, but it's determined with the sum from the observed minus the expected divided by the expected, and of course from I equals 1 till the last one. Same thing. And the conditions and the requirements are the same. All counts are more than or equal to, or expected counts must be more or equal, at least 1. Okay, so all these EI, the expected counts have to be greater than or equal to 1, and also not more than 20% of them are less than 5. So not more than 20% of them, not more than 20% of expected less than or equal to 5. We don't know, not known, till I conduct the test, unfortunately. So for all the other tests, we tested, they had the conditions of the test, we verified independence, we determined normality before we conducted the test. Here we cannot do that. There is no way. We have to determine, we have to conduct the test and then say, oops, I cannot really use this test. Or say, yes, the test is okay, I can apply it. Conditions are fulfilled. So let's see how this works. Let's look at the first problem. And I think we did this problem last time, but let's do it again because I didn't get the chance to show you with StatCrunch or anything else. So here we have, is there a relationship between marital status and happiness? And we have the table. So marital status is married, widowed, divorced, never married. Very happy, pretty happy, not too happy. So I see in this problem, so in example 3, I immediately say rows 3, columns 4. I will conduct a chi-square test, but how many degrees of freedom? 3 minus 1 multiplied by 4 minus 1. And that is 2, and this is 3, so 6 degrees of freedom. Do I know that the expected are greater than or equal to 1? No. Do I know that not more than 20% of all the answers which I will have, how many expected values? 3 times 4. So it will be a matrix of 3 by 4. 2 different matrices to be exact. One for the expected and one for the observed. By the way, this is what this means. Observed. By observed this is what we have in the table. All these data are observed. We observe them. And this is the expected. What does the expected mean? If the null hypothesis is true, we expect the numbers that we will come up with in a minute. So if those two numbers, the observed and the expected, are very close to each other, the variables are most probably independent. But if these two numbers are so far away from each other, the observed and the expected, we will most likely reject the null hypothesis. And I'll come back to this test. Let's conduct this one first. Okay. I'm going to write the matrix here so everyone sees what I'm trying to do. So this is our matrix, and we are going to enter it in matrix A or any letter you like in your calculator. It doesn't matter. So I have 663, 112, 144, 720, 142, 355, 459, 93, 51, 119, and 127.